Thank you everyone for joining today. So let me share my screen and let me make a short introduction of myself and our speaker. So yes, Susanna said correctly, I'm kind of working in several positions right now, and I helped with several events in the past. And in my deep past, I worked in one of the biggest, I believe, IT companies in Europe called Yandex. Maybe some of you heard about that company because of self-driving cars, which it's running successfully, and some other initiatives. But company was started many years ago in the 90s, and from the early beginning, main business of Yandex was related to machine learning. It was a search engine. However, year by year, company grown up, and I think currently Yandex has many businesses which empowered by machine learning. And because company grown, of course, amount of data consumed by machine learning pipelines grown too. And Yandex constantly invested into open source and inner source machine learning projects. I even used some of them when I worked at that company. But of course, we invested not only in machine learning algorithms and scientific part, they also invested into data labeling, which is, as you know, essential part of machine learning pipelines. And around 2015, Yandex realized that experience that they basically accumulated during years and years of working with massive data sets and labeling, all this experience can be shared with other people. So we dedicated basically that inner part of Yandex, which makes data labeling as Toloka. And Toloka, this is a company who represents that like quintessence of Yandex experience and labeling. So that's where our guests came from. So please welcome them, Dmitry, and let me hand over to him so he can continue.
Yeah, hi everyone. I hope you can hear me well. Give me a few seconds so I can share my whole screen with you. And okay, I'm ready to go. All right. Thank you for the very warm introduction. It's a very great honor to me to talk at this meetup. And let me tell you some story about data labeling at scale, about information retrieval, and the possible applications that you can actually make using the same techniques on a different kind of data. So my talk will be all about data labeling for search relevance evaluation, which is the classical task arose from information retrieval. So you have a machine learning model, which is the de facto technique for ranking results, and you want to improve it by using data. And you have some preferences of people, and you need to carefully take them into account. So after my talk, you will be able to implement a similar approach that uses crowdsourcing to improve the quality of your e-commerce applications, of your recommender systems, of your search engines, and so on. So the same technique works really well for different domains and different data sets. And one slide about me. My name is Dmitry Ustalov. I live in St. Petersburg, Russia. I'm the head of research at Toloka. Our team is responsible for spreading the innovations made by the Toloka team to the entire world. And at the same time, we are constantly working on improving the quality of crowdsourcing annotations and in general annotation quality in Toloka. And in the past, I was researching a lot in the field of natural language processing. In particular, I was interested in computational lexical semantics, how words are connected to each other and how to evaluate them. And after that, I found that crowdsourcing is a great way to learn from people's preferences. And after that, I shifted towards this phenomenon instead of focusing on NLP. And here's the outline of my talk. we will start from a short introduction to make sure that we are on the same page. We break the ice, we provide some context. Then I will discuss the pipeline that we will implement and we will focus on. After that, I'll show you a lot of things, a lot of technical information useful for your further developments. So let's start with the introduction. And again, information retrieval is a very, very broadly defined field. It's the discipline that builds search systems. And the state-of-the-art approach so far is machine learning, that you perform ranking, you sort documents using some trained and properly evaluated machine learning problems. You need huge collections of documents to properly train your model. For example, if you have a web as a corpus, you have a lot of data, but you need to handle all the queries that are sent by people who are using your engine. And today we'll discuss how to obtain information retrieval, or IR, evaluation data with human in the loop at scale. And this is actually a follow-up from our tutorial at the WebConf tutorial last year. Human in the loop is a methodology that intertwines the process of doing a task by combining people effort and machine effort. So you combine some manual steps with some automated steps. And this is very important for us today because we have this pipeline. We have this cycle in which we have a ranking system that performs ranking of your documents. Then we perform several steps related to machine or other kinds of processing. And as a result, we have the evaluation metrics. So we have the quality of our search engine, and we have the data to improve it. And let me show you what this problem is. You have a screenshot of some information retrieval system. We call it Yandex. And people type their query. For example, expected reciprocal rank. There is a query. And then usually a search engine outputs a list of items. And in case of information retrieval on the web, you usually obtain the list of web pages. And the higher the position, the higher the confidence of the system that this is the best option you get. And given the query, this system outputs the ordered list of items. And you need to know, and you need to make sure that this is consistently good. And here we have many, many challenges. So relevance, so the documents must be relevant. Timeliness, which means that you need to constantly bring the fresh documents to your output. You need to scale to a huge variety of queries. You need to be careful about evaluating it and so on. And one of the approach is called offline metrics, in which you sample queries, you sample the results, and you evaluate them using the technique I described. And let me dive deep in this figure. We have this query, expected reciprocal rank. So this is what the person asked the system. Then it tries to output something. And some documents are explanations of what it is. Some are irrelevant because mean and expected here are two different metrics. This is the simpler version of it. And this is the one that has some probabilistic foundations behind it. Here's the original paper that described this method. And usually people don't read after maybe 3 or 4 first item on the search engine results page. So we have this very difficult problem. We have infinite numbers of queries. We have different infinite numbers of documents, but we need to make sure that we can serve people. And one of the most classical approach here is to compute a kind of evaluation criterion. One of the examples of them is normalized discounted cumulative gain, NDCG, which is a classical formula that tries to compare your order of the items with the ideal order that is defined somehow. And suppose that you have some items and you have grades of them. So the higher the grade, the better the item is 2 is better than 1, 1 is better than 0, and so on. And the ideal system puts items with the highest grades first. So ideal ranking is this: 2, then 1, then zeros, and so on. And you have two real systems that output some results. And after that, you can compute the NDCG formula to make sure that one of the systems works better than the other one. And in this example, we have that system B has the higher number of NDCG, and it provides somehow better ranking than this. But in order to evaluate your system, you need to build this ideal ranking. And that's what we will do today and right now. And indeed, NDCG has been invented a long time ago. And here is the paper related to this technique. There are some other metrics, but basically you almost always want to have this ideal ranking. And that's what we will get today. When it comes to NDCG, I have to add a few comments. It has two issues. First, if you have the infinite number of items, it will converge to 1. So here is the theoretical study shown at the bottom of my slide. And here they show that you will always have 1 if you have an infinite number of documents, which is undesirable because, well, you need somehow to restrict yourself to make sure that results are reasonable. And there are two ways to handle this. First, you can use the different discount function. From the logarithm, you can use some power transformation. And also, you can limit the number of top key documents. So instead of computing the NDCG for all the documents you got, you fix some k, a hyperparameter key, and then you use a limited number of top documents to make sure you're doing well. And that's the core idea here. You perform sampling. And by sampling, you can limit yourself to a reasonable number of items to evaluate. So you have an information retrieval system or some ranking system that outputs ordered lists. And you want to know whether you're doing well or not. For this, we need sampling. And right now, I will show you how to do it. How do you sample queries? And offline evaluation means that you have this data downloaded and fixed. It can be done every day or every minute or every hour. Regardless of this, you are not working with your system at all after extracting the data. So it's called offline evaluation. Otherwise, it will be online evaluation with A/B tests and so on. It's not the topic of our today's talk. And how do we sample queries? Here are some heuristics. You can sample only the most popular queries, like the ones that are always asked, maybe weather, maybe some other key topics, and it does affect a lot of users. However, you will not be able to represent the whole distribution of your queries. You can look at another part of the tail of the distribution. You can pick only unique queries, so the queries that are infrequent. They are usually hard, so if you do well on hard queries, it's a good thing. But however, it requires you to lower the amount of attention you pay to the most of your users. Indeed, there are huge amount of unique queries in the wild, but it's not what you want. And maybe something in the middle, so it's a reasonable choice. And the core idea here is, indeed, you can just flip coins and perform sampling, and you will get some sample of your queries that might resemble the general population. And instead, you can use reservoir sampling. That's very well described in the research papers, that requires you to take into account every object, and you will have the guarantee of the number of selected objects. But however, the better approach, as according to our experience, is to perform stratified sampling. You have the frequencies of the queries, and you first order the queries by splitting them into buckets, and then you sample the necessary amount of items from the buckets. So you look at the data first, you look at the buckets, and then you sample from the buckets. It guarantees that you will have a representative sample of all the queries you might need, which is a very important property because you want to achieve a generally good quality of your data and of your model indeed as well. And it's not enough to sample one basket, one set of baskets. You actually need 3. You need the KPI basket that contains the data for overall quality evaluation. So you make decisions on whether you are better or not based on this basket. Another one is validation. So it's similar to machine learning. You have regular evaluation, use some measurements, fine-tuning of your models. It's done on validation set. And some test basket for sanity checks. They have to be similarly sampled, but they must be independent from each other. So you won't overtune or overfit your model on this. And the key issue here is that you need a frequent update of them. News change every day, and you might want to make sure that the sampling process can be run on the same velocity as your data is generally changing. So right now we know how to sample queries. And at the beginning, I told you about something related to human in the loop. And right now we have the system that works. We have a sample of queries and documents related to every basket we have. And now we want to ask people about their very subjective opinion about whether the ranking is optimal or not. And here is the place where we use crowdsourcing. Let me show you the crowdsourcing task. We use independent judgments from people who perform different tasks on a crowdsourcing platform. It might be Toloka, it might be anything else. The core idea is the same. You ask the crowd. And we, at Yandex internally, we use a mix of public crowd, Toloka, and internal in-house crowd to get the best results depending on the domain we have. But indeed, Toloka is one of the places when you can surely do it. And how it works in practice. We have this training data, and we have multiple versions of our model. We perform 2 kinds of evaluations. We perform offline evaluation, which allows us to run an infinite number of experiments using the same data and to choose the better one. And at some point, we will see that, okay, this one doesn't work really well. These 2 behaved better. And after the offline evaluation step, there is an optional step of online evaluation, which is super important because a model trained on offline data is still trained on a subset of data used before. Maybe today world is so different, so it won't be super efficient. So we have online evaluation step. After that, after 1 day of being in production, by production, I mean being run on the very same infrastructure that holds the whole engine. It goes into production, and then we performed 4-hour KPI evaluation on the KPI basket. So after that, it becomes the new model that serves the majority of users. So it's gradual deployment plus offline evaluation. And here's the offline evaluation part that we are interested in. And here is the slide that shows you the task. Let me explain how it works first. We have a query and we have a region, for some example, because there are some different domains, there are some different aspects of the information retrieval that you need to really take into account. And here we have a query and a region. And all the people have to do is to look at these 2 figures, A and B, left or right, and say which of these 2 answers the original query better. The query is catering disposables, and here are 2 responsible for this. And you need to select whether you like more, left or right. By giving this simple task, we achieve the possibility to rank these lists. And I'll tell you a bit more about transforming these pairwise comparisons into lists of usable items. But first, I'll show you how it works in Toloka. So I hope you see my screen well. So here we have the Toloka interface for the requester, in which you select the pool that contains the data you are currently annotating, and it contains the complete setup of the task. You have about 10,000 people in the current settings that you set for the audience, price, and skills required from the annotators. You also have the trade-off between speed and quality. There are some possibility to see the statistics, but since we have not received any annotations, it doesn't matter. Here is the interface of the task. First, we describe the instructions have to be obeyed, and here is the example of providing response, whether you like more left or right. So here are these examples. And after submitting the response is recorded, and the person who submitted this response receives money for their very valuable contribution to information retrieval evaluation. It's possible, after checking that if everything's fine, to start the annotation. So you'll be paying money for doing this. And here are some progress of running the stuff. It's indeed sped up, but usually it's also quite quick. Here's the amount of money spent for receiving these labels, and we have indeed some feedback from those who provide this task. And let's look at the responses provided by the people. And here are, you've seen this fan figure before, and you see that the response was left to right, left to right, left to right. Okay, after you got all the responses, or in the middle of the annotation, you can download the annotated data, and you can also use a library called CrowdKit. I'll tell you about it a little bit more to make sense of these comparisons, of these pairwise questions. So, and after running this, we obtain the data that we can use to actually evaluate the quality of our information retrieval system or recommender system. Okay, so I think I can stop. So that's the core idea. We ask a very simple question, and now we need to make bridges between what I told before and what I'm telling you now. But let's finish the crowdsourcing part first. So since you're running a task on a public crowd, you need to make a few steps to make sure that the output quality will make sense. And we found that the quality of the annotation is influenced by, indeed, the quality of the instruction, because if the person who performs your task is doing it online and it's happening online, all they have is the instruction text. They cannot reach you and receive the immediate response because you might be offline at this moment, unfortunately. So they have to have a good instruction. Then you need to make a good golden tasks. These golden tasks are the tasks that are pre-annotated by the requester, so by you, and you need to use them to filter out those who can be sloppy or inaccurate in making these responses. You can use synthetic data indeed. It is also affected by performance selection, by performance motivation and rewarding, so it's a very multi-dimensional problem. But generally, you need to do this continuously. So you run this process, and we are running this process all the time to make sure that our relevance judgments are up to date and accurate. So now you have sampled your queries and the documents. You ran some annotation process that allows you to obtain the pairwise comparisons. So for each query, you pick a set of documents and you compare each of them, each pair of them with the crowd. Now you might want to transform these pairs and the responses you got to the meaningful lists to compute the evaluation metrics. And that's what we will do now. It's called answer aggregation. This is the core idea. If you have performed crowdsourcing tasks before, you might want to use the setup called classification. For example, please rate this item for this query. Very relevant 5, not relevant 1. So it's a graded relevance. It's a very classical task. However, when you compare items, the latent label assumption is not satisfied. What it means? It means that in classification tasks, you assume that there is only one correct response, for example, very relevant, and this response is clearly explained in the instruction. At the same time, the pairwise comparison tasks cannot guarantee that because they are designed by initially to handle subjective information, and subjectivity just ruins this assumption. So different tasks may contain common items, which will again break this assumption. And fortunately, there is an approach called Bradley-Terry model that I will present you right now. So we have two kinds of answers, left or right, and we have a set of items. And we have a set of pairwise comparisons for these items in your data set T. And we want to obtain a ranking P over these items that is based on answers in this P set. Here is the Bradley-Terry model that was designed back in the 50s, many years ago. And it performs a very meaningful thing. It assumes that each item has a latent quality score. You see that? Okay, so now you have items with quality scores, and you can infer these quality scores by computing probability of being preferred, and then rank these items based on this quality score. Here is some, pitfall. This model assumes that all the annotators are equally good and truthful, which is unfortunately not always true. And since this model was invented back in the 50s, you can observe a lot of variations and a lot of improvements that try to address this problem. One of the solutions is called NoisyBT, and it works like that. We assume that not just items have parameters of quality, but we assume that the annotators also have them. They have two parameters, reliability and bias. And we modify the likelihood of this model in such a way that we include these parameters into account. And then we optimize this likelihood using, for example, gradient descent. And as a result, you can observe that even the performer, so the second person, always answers the left option, which is unfortunately not very good. We found this. We see that this skill is 0 and the bias is high. So bias is the chance of answering only one left label. I said this issue is handled entirely. However, there might be others that might be missed by this model, but still is better than before. And so only the responses from the first person are taken into account. And this person said, okay, between A and B, I choose A. Between B and C, I choose B. Between C and A, I choose A. So A is the best option. The second is probably B, and then C. Let's see. First, second, third. Well, it makes sense. And that's the core idea. You perform pairwise comparisons, then you aggregate them. And by aggregating them, you have a list of items. And now it's trivial to compute any metric designed for comparing lists of items on these two lists of items. That's the core idea. The pitfall is you need to write code to do it. It's not true now. We have released an open source Python library called CrowdKit that implements all the algorithms I mentioned and some more. For example, if you are dealing with crowdsourced data often, you might be really interested in running it. It's even available on PyPI. Under an Apache license, it includes all the popular methods like majority vote, some probabilistic methods like David-Skin and Bradley-Terry. It also has some embedding-based methods for text aggregation like RASA, HR RASA, and language model-based techniques. So it's very handy, it's very general purpose, and we use it every day to ensure the quality of our annotation. The only question remained is how do we select pairs? Okay, remember, you have the system, you have the samples, you have for each query a set of documents. We want to run a pairwise comparison task on a crowdsourcing platform, but we need somehow to sample the pairs. And indeed, it's a big question how to do it. There is a straightforward approach for doing this, we can just compute the number of combinations and take n² comparisons where n is the number of objects in your query. It's expensive. You might not want to do it. But instead, there is a way to compute a subset of these pairs. In particular, like you are doing with, for example, quicksort algorithm, you can take n logarithm n comparisons. And here is the way to do it. It's enough to use n log n comparisons if all the comparisons are transitive. So if you can build a connected graph with these comparisons. However, it's not always true. In crowdsourcing, the comparisons might be with broken assumption. However, we can assume on the following feature of the Bradley-Terry model. If you have 3 items, and these 3 items have the scores ordered, you can assume that everything is fine with you. So the answer is the following. How to choose pairs? If you look at this figure, you'll see that suppose that there is ground truth ranking of items. So the color is the value of your for example, is just a value. And you have a random ranking. So it's a kind of baseline that you just sample randomly from the top line. And suppose that you are running a quicksort algorithm, and a step of the quicksort algorithm is a pairs comparison. And since these comparisons are noisy, and as they are obtained from the crowd, you find kind of this. And that's the idea. So the lower bound is n log n, the upper bound is all the possible pairs. And the reasonable choice to make sure that your algorithm will still provide meaningful results, having preserved the transitivity assumption in a reasonable way, is k n log n, where k is a hyperparameter that needs to be tuned. But usually our experience shows that it is enough to pick maybe 12 or more, something between 2 and 12. And that's it. So now we know how to deploy our ranking system, how to sample queries and documents from it, how to run a crowdsourcing task, how to aggregate the data and properly sample the pairs. And then we can compute metrics, any metrics we may want to compute to compare lists of items, NDCG, pfound, expected reciprocal rank, and so on and so forth, any metric you might want. And now there's a conclusion. So now we have everything and we compute everything. It's worth mentioning a few takeaways. First, the quality of machine learning-based products depends on the data. And if you can achieve a high velocity of data processing, if you have reasonable volumes, you can be successful in delivering this model and the value based on this model. And crowdsourcing surely allows you to do it. Second, crowdsourcing allows you to obtain training data faster and cheaper and at any scale, because you have a lot of people available and willing to solve your tasks and just upload the data and provide the reasonable instructions and quality control configuration. And with crowdsourcing, it's all about trade-offs. You have to find a trade-off between accuracy and data set size. And there are some really difficult tasks that you cannot solve using crowdsourcing and you use managed crowd instead. But generally, it's a good idea to use it because your tasks are usually simple. And indeed, it's not necessary to juxtapose crowdsourcing with managed crowd, because they can build pipelines, like I showed in the beginning, that benefits from everything. Okay, in the end, I want to highlight you a few useful resources. The first is the data set of text retrieval conference data, track, which is a very important conference that actually set all the quality baselines and evaluation campaigns for search engines. At Toloka, we have released a very nice set of data sets called Toloka Relevance 2 and 5, based on the number of grades of evaluation that you might use for evaluating your systems. Here are some references I mentioned throughout my talk, and that's it. Thank you very much.